So this video will look at day 10 in our packet for Algebra 2, and day 10 focuses on the fundamental theorem of algebra. And the first thing we're going to look at here is, have we noticed any polynomials that have repeated solutions? So pause the video, take a second to see if you can think of any, and then when you start the video back, I'll put one example up here. So the example I thought of was about x squared minus 4x. Well, does that have any repeated solutions? If we think about it, if we were to factor this goes to x squared minus 2x minus 2x plus 4, because two numbers that multiply together to get 4 add to get negative 4, and what you end up seeing is that x minus 2 times x minus 2. So if we were solving for this, it would become x minus 2, 0, so x is 2, and we do it again, x minus 2 equals 0, x is equal to 2. So what you see there is the two solutions are the same thing. So that's important because it helps us establish the fundamental form of algebra. So first, here's what it says. For every polynomial f of x, that polynomial has at least one solution. And so to go off of that, if you count repeated roots, so that's like what we just saw where x equals 2 appeared twice, the number of times they appear, so we would count that as two different solutions. Each polynomial, and if we denote that as f of x, has the number of solutions equal to the degree of the polynomial. Interesting. So let's talk a little bit about what that means and look at an example. So here, if we have f of x is equal to x cubed plus x squared plus 3x plus 3, how many solutions should that have? And if you look, okay, the degree here is a third degree polynomial, right? It's a cubic function. So we would expect 3 roots. That's what we're expecting, right? We're expecting 3 roots. Again, roots is the same word as zeros, which is the same as solutions. They all go together. So how would we find that? Well, in this one, we could factor by grouping, right? F of x would equal x squared times x plus 1. Bring out the 3, so plus 3, x plus 1. So x squared plus 3, x plus 1. And at that point, when we're actually finding zeros now, so x squared equals, or x squared, sorry, minus plus 3 equals 0, and x plus 1 equals 0. So when I solve, x is equal to negative 1, and x is equal to plus or minus, and this will end up being I square root 3. So there, did we get 3 different roots? Well, we got negative 1, which is 1. But then we also got plus or minus. So this will count as 2 different ones because we have the positive version and the negative version. So now, why don't you take a second to try number 2. How many solutions should you expect to get? So again, here you should expect 3 solutions because it is a cubic function, again, degree 3. Okay. Again, we have all the different ways you can try to factor it. You can do this by grouping. If you try that, you could try doing P over Q, all the different methods that we've done before. So why don't you try that, pause the video, when you start the video back up, you'll see the solution there for you. If you look at different ways to factor, the way that I came up with is we have to do P over Q here. If we check the shortcut by adding all the coefficients, it does not equal to 0, so we're going to have to do it the long way. But the one thing that we can see is that all the coefficients here are positive. And since they're all positive, we know the solution will have to be negative. So we have only really need to check negative 1, negative 3, and negative 9. So if we start with negative 1, 1, 7, 15, and 9, drop this down. There's 6, negative 6. There is 9, negative 9, 0. So luckily negative 1 works. So when I rewrite now, f of x equal to x plus 1, that comes from the negative 1 working. And what I would be left with is x squared plus 6x plus 9. And if you now can factor that quadratic using the A times C method, you should see that it's going to be 3 and 3, because 3 times 3 is equal to 9, and 3 plus 3 is equal to 6. And when I factor this, right, I'm going to just go to x plus 3 and x plus 3. So now we're able to just set each of these equal to 0. X is equal to -1. X plus 3 is equal to 0, so x is equal to -3. And x plus 3 is equal to 0, so x is equal to -3 again. So if we were to answer this question, okay, how many roots are there? Well, there are 3, but 2 of them are a repeated root, -3 appears twice. So really, if I were writing the answer, I would only have to include -3 once and +3 once. So there's the difference, okay? It's always good to show all your steps and show the repeated roots, but then if it asks you to simplify it down, this would become your answer. So now, piggybacking off of this, we can look into this complex conjugate theory and irrational conjugate theory, and they're very similar. So one will deal with i's, or imaginary numbers, complex, and the other one will deal with square roots. And what it pretty much says is that if you're given 1, 0, and it is a complex number of the positive version, so it's plus the imaginary part, you will also know that the negative imaginary part right here is C, this one will also be part of that function, right? And then the same thing happens but with the square root. So you got it there and there. And that just, I can highlight that so you can see it. So here and here, as well as there, right? So you can see that going on there. So now if we come down, let me just show you what I mean here. So, and it won't be in the first problem, but it will appear in the second problem. So write a polynomial function of least degree that has rational coefficients, a leading coefficient 1, and given zeros. So what this means is you're given these zeros. What you should do is create factors, and then from that we will expand them to get one polynomial. So how this is going to work is we'll say, okay, some polynomial f of x is equal to, well, the factors that will give us these zeros. So the first factor is x. To get -1, we have to do x plus 1. Then to get 2, x minus 2. To get 4, x minus 4. And now we're just extending these. There are lots of different ways to do it. I'm going to use FOIL at the beginning, and then I'll use the second way. So first here, x squared, outside -2x, inside x, then last minus 2. So this is still being multiplied by x minus 4. Let me combine my like terms. So x squared minus x plus 2, x minus 4. And now we might use the box method here just to make it a little simpler. I always like this when I get above a binomial. So x squared negative x and 2x negative 4. And remember, all you do is multiply them where they meet. So x cubed, excuse me, sorry about that. And then we get negative x squared 2x negative 4x squared 4x and negative 8. And as you see with these, we've done this before. Work here. Do that. So what we do at this point is we'll add just across the diagonals as you see there. So this becomes x cubed negative x minus 4x squared, so 5x squared, 2x plus 4x is plus 6x, and then minus 8. So what we're doing here is we're doing the reverse of what we have been doing, which is factoring. Now we're just using the roots that were given to expand. Okay, so that was the beginning. Now we're going to look at number 2 here. I'll change those just so we can keep them separate. And we're given the 2, 4, and 1 plus root 5. Well, 1 plus root 5 will follow this irrational conjugate theorem. And I'll show you how to do that here. So this, again, same idea. Okay. The first thing I would do is, since we have positive version here, we have the positive version. I highlighted too much. I apologize. I'll adjust here my colors, what I have going on, and it should help us out a little bit. So I had the positive version. So what I need to do is I need to add the negative version to this. So if I add the negative version to this, I will have 1 minus square root 5. So I add that in there. And now I'm just following the same steps I did earlier to make this x minus 4, x minus 1 plus root 5 times x minus 1 minus root 5. Now, this is going to be a little trickier, and normally what I'll do here is I will actually work with this complex or the imaginary part first. So we'll do x and negative 1 plus square root 5. And then same idea going down the side here. So this will be a little bit trickier. Okay? And we do have to treat those negative 1 plus or minus the square root of 5 as binomials. So it ends up being negative x plus x root 5. Same thing here, negative x minus x root 5. And then to go in this last box, we'll actually have to FOIL these two. And 1 minus root 5. So what you see is negative 1 times negative 1 is 1. Okay. We get plus root 5 minus root 5. And then the square root of 5 times square root of 5 is negative 5 because it's one of them's minus. And so you get 1 minus 5, which is, in this case, negative 4. So that becomes a negative 4. Now when you add across, I get the x squared negative x plus x root 5 minus x root 5 minus 4. But we can still combine some like terms here, the x and the x, the plus root 5 minus root 5, and those two will become 0. So x squared minus 2x, the x root 5s are now gone, and then minus 4. So what you see there is from that, we get back to this equation. And if you were to factor this equation, you would get back to the roots that we started with. Now the same thing, I'll help you set up number 3 and number 4, but I'll let you finish them on your own. So here on number 3, right, now if we scroll up, we're looking at the complex conjugate theory, where we're given, in this case, we're given the minus, so we need to add the plus. So first thing, just add 3 plus I, and then when I set it up, from that, so now it's x minus 3, x minus 3 I, x minus 3 plus I. And what you need to make sure of, again, you're treating that 3 minus I, 3 plus I as binomials. If you look at number 4, so pause the video, look at number 3, but if you're looking at number 4 to set it up, okay, I have an imaginary part. Okay, so what do I need to do? Normally we make the imaginary part negative, so we'll do that again. So now adding 2 minus I, or minus 2I, as a root, we also have a rational part. So we'll add 2 plus root 2 because it gave us the negative, so we need to add the positive. And now you can set that up as well. So if you want to see how these problems turned out, you can look on to our haiku page where they will be there. So hopefully this helped, and I'll see you back in class on Monday.